You can think of a refrigerator as a small, sealed box air conditioner. Both work by using refrigerant to move heat from a low-temperature environment to a high-temperature environment. But why can a refrigerator drop to as low as -10 degrees or even lower? Let's take a look at the entire working process of a refrigerator and you'll understand. Just like an air conditioner, the core structure of a refrigerator also consists of a compressor, condenser, throttling device, and evaporator. First, low-temperature, low-pressure refrigerant gas enters the compressor. The compressor is the engine of the refrigerator's cooling system. Refrigerators generally use fully enclosed reciprocating piston compressors, which contain a motor, crankshaft, piston, and other parts inside. They're compact in structure and run stably. Through 3 steps, intake, compression, and exhaust, the compressor squeezes the low-pressure refrigerant into a high-pressure gas, with its temperature shooting up to around 70 to 80 degrees Celsius. This high-temperature, high-pressure gas then flows to the refrigerator's condenser. In traditional refrigerators, the condenser is that big black coil on the back, which releases heat through natural convection. But that design takes up space and looks unattractive, so many modern refrigerators now hide the condenser inside. The refrigerant then becomes a high-temperature, high-pressure liquid and flows into the dryer filter. Inside it are desiccant pellets with strong moisture absorption capacity, as well as porous metal mesh or ceramic filters, which protect the cooling system from damage caused by moisture and impurities. Next, the refrigerant enters the throttling device. Unlike air conditioners, which use adjustable expansion valves, refrigerators usually use a simpler capillary tube. This is a thin, long copper tube that can be several dozen centimeters or even a meter or 2 in length. Its thinness and length are designed to gradually lower pressure and control flow, so the pressure drop isn't too sudden or unstable. Inside the capillary tube, the refrigerant is still in a high-pressure state, but once it sprays into the evaporator, its pressure suddenly drops to a very low level. Part of the liquid flashes into gas, becoming a low-temperature, low-pressure liquid-gas mixture. This sudden pressure drop causes the refrigerant's temperature to fall from about 40 degrees Celsius down to around -25 degrees Celsius. After that, the refrigerant enters the evaporator inside the refrigerator. Here, the refrigerant begins to boil and evaporate through direct cooling, not boiling like on a stove, but naturally turning into gas under low temperature and low pressure. During evaporation, the refrigerant absorbs a large amount of heat from inside the refrigerator. At the same time, it becomes low temperature, low pressure gas again, then flows back to the compressor to start a new cycle. In this way, heat is gradually transferred outside the refrigerator. Plus, with its sealed and insulated structure, the refrigerator achieves the cooling effect we experience. However, when the water vapor in the fridge air touches the evaporator pipes at temperatures below 0 degrees Celsius, it condenses into droplets. After further cooling, these droplets freeze into ice or frost. Too much frost reduces heat exchange efficiency, which actually lowers cooling performance. That's why most modern refrigerators use air cooling combined with automatic defrosting to prevent ice buildup. The principle of automatic defrosting is simple. A defrost heater is hidden around the evaporator. When it's time to defrost, the refrigerator's control system powers the heater, raising its temperature to several dozen degrees. This melts the frost or ice on the evaporator surface into water, which is then drained away. Subscribe to us for more amazing analysis.